Having learned why organic reactions take place, it is now time to learn how to keep track of electrons using curly arrows by taking basically examples. Now in this regard, we have to watch out that elements in period 2 such as carbon, nitrogen, oxygen, okay, have to obey the octet rule. The hydrogen has to obey the duet rule. Let's take, for example, a radical type reaction where a bromine radical, for example, that's a bromine radical, reacts with another bromine radical. In this case, the type of arrow that we should use is the half-headed arrow, if you like, okay? So what we need to do is we need to move an arrow from that single electron to that arrow is half-headed, which indicates movement of a single electron. So where is that electron going? It's actually going to unite with the other electron coming from the other bromine radical. And again here we have to use this type of arrow, which is indicative of a single electron movement. So in both cases, in both reactions, if you like, of these two radicals, we have to use a half-headed arrow. Now, the two electrons unite with each other to make a bromine-bromine bond. And this is the new bond that has been formed. That's the new bond. Again, remember, you need two electrons, either homoletically or heteroletically. Homoletically as in radical reactions, homoletically as in polar reactions, which constitutes the vast majority of organic reactions. So this is a radical type bond formation reaction. Let's now take examples of polar reactions. Again, trying to learn more about the use of curly arrows or the use of curved arrows, trying to acquire this skill, okay, of using these arrows to indicate electron movement. Let's take, for example, a reaction between the cyanide ion and this alkyl halide. So again, these two reactants, the nucleophile, the cyanide ion, interacts with the electrophile, the alkyl halide, at this electrophilic site, as you remember, and that's due to the difference in electronegativity due to inductive effect, due to inductive withdrawal by the halogen. So what happens is that the two electrons from carbon, being the nucleophile, will now go and attack that electrophilic site. And please watch out the strict movement or the strict indication of the electron movement represented by the curly arrow. The two electrons move from carbon. It's a doubly headed arrow which indicates movement of two electrons. So where are these two electrons going? They are going to attack that carbon, and at the same time this CBr bond must break, because carbon now in the alkyl halide has 8 electrons. It obeyed the octet rule. Carbon cannot be surrounded by 10 electrons. It cannot be surrounded by more than 8 electrons, and therefore the CBr bond must break simultaneously at the same time. So the product will be this, and it is clear that that bond is the new bond. So the valency rules are obeyed. This is something that we have to watch out always whenever we want to keep track of electrons, or whenever we want to draw possible mechanisms for organic reactions. This is another example. So this is a carbocation. If you react the carbocation with a nucleophile such as a neutral one, such as water. Now water behaves as a nucleophile in this case because it has a lone pair. So the arrow should move from the nucleophile always to the electrophile, and not anywhere in the electrophile. It's obvious that it has to go to the electrophilic site due to inductive effect or resonance. Yeah. Okay, so this carbon, since it's positively charged as a carbocation, the positive charge is actually on carbon. So the arrow should move from the source of electrons, from the nucleophile to the electrophile, from the electron-rich site to the electron-poor site, to give a covalent bond. So something like that should be produced. So that's the new CO bond. And now oxygen normally makes two bonds. The formal charge of oxygen here is actually 0 because it has 6 valence electrons, 4 non-bonding electrons and 2 bonding electrons. That's 6. If you subtract 6 from the usual number of valence electrons of oxygen, you get 0. So 6 minus 6 is 0. The formal charge in this case is 0. If you look at this oxygen has a lone pair. One lone pair has been used already to make a bond between oxygen and carbon. But if you count the number of valence electrons in that structure, you'll find it's actually 5. So 2 non-bonding plus 3 bonding electrons, that's 5. If you subtract 5 from the usual number of valence electrons in the free state or the free atom, which is 6, you get plus. So the formal charge is actually plus 1. So it is positively charged oxygen in that intermediate product. Let's now take another example. Of an organic reaction to illustrate the idea of using curved arrows or curly arrows to indicate electron movement, to be able to understand reactions, if you like. So if we take, for example, again, the cyanide ion, and we bring it in contact with that aldehyde. This is a very general representation of aldehydes. The cyanide ion attacks carbon, obviously, of the aldehyde, and that's due to inductive effect, inductive withdrawal by oxygen, as you've seen before, and also because of resonance. That carbon is the electrophilic site. So the curly arrow should go from the nucleophilic site in this nucleophile to the electrophilic site in the electrophile in general, which is an aldehyde in this case. So the product will be this basically. Now, if you look carefully at the electron movement indicated by the curly arrows, we moved an arrow from these 2 electrons to the electrophilic site. So this indicates or means, okay, 2 electrons have now moved. They've been used to make a bond between carbon and that carbon, to make a covalent bond. But we know already that carbon, in this case in the aldehyde, is surrounded by 8 electrons. Carbon cannot be surrounded by more than 8. So this carbon-oxygen double bond must break at the same time to maintain the valency, or to keep the valency rules, or not for carbon not to exceed 8 electrons. And that's exactly why the carbon-oxygen double bond must break at the same time of the nucleophilic attack on the electrophilic site, and we get that intermediate product.